Space is often described as a silent void, a vast emptiness stretching between stars. But this silence is deceptive. It is a silence filled with tension, tension that builds across the vastness of the cosmos, like the faint rumble of a distant storm yet to break. Out here, where gravity rules and light bends, stars live and die in violent, beautiful ways. Most stars burn steadily for billions of years, fusing lighter elements into heavier ones, giving birth to the elements that make up everything we know, ourselves included. But some stars end their lives in explosions so powerful they shake the very fabric of space-time. And from the ashes of these titanic explosions arise objects of extraordinary density and power, neutron stars. Among them, a rare and enigmatic breed exists, magnetars. These are neutron stars cloaked in magnetic fields so intense they defy imagination. What are magnetars? How are they born? And what happens when their immense magnetic fields snap and fracture? Tonight, we journey into the heart of cosmic quakes, unveiling the destructive power of magnetars. The story begins with a massive star, tens of times the mass of our Sun. For millions of years, this star burns fiercely, fusing hydrogen into helium, then helium into heavier elements. But every fusion process brings it closer to its inevitable fate. When the core runs out of fuel, gravity takes over. Without the outward pressure of fusion, the star's core collapses under its own immense weight. Within seconds, the core shrinks from thousands of kilometers wide to a sphere just 20 kilometers across. A neutron star is born. The outer layers of the star, no longer held by gravity, explode outward in a brilliant supernova. A final, magnificent farewell to a dying star. But the neutron star left behind is unlike anything else in the universe. Imagine squeezing a mass greater than that of our Sun into a sphere the size of a city. The matter is so dense that a single teaspoon would weigh as much as all the buildings in a city combined. Many neutron stars spin rapidly, sending beams of radiation sweeping across the cosmos like lighthouse beacons. These are pulsars, the cosmic clocks of the universe. But a tiny fraction of neutron stars form with something even more remarkable: magnetic fields 1,000,000,000,000 times stronger than the strongest magnets humans have ever created. These are magnetars. Their magnetic fields are so intense, they dominate everything else. They twist and distort the space around them, influencing particles, atoms, even the vacuum of space itself. The origin of such staggering magnetism lies in the chaotic birth of the star. As the core collapses, the magnetic field lines trapped within are squeezed and intensified, spun faster by the rapid rotation. The star's interior acts like a cosmic dynamo, amplifying magnetic energy to levels beyond comprehension. But with great power comes great stress. The magnetar's surface is a solid crust of iron and exotic matter, but the magnetic field beneath exerts enormous pressure, twisting and stretching the crust like tectonic plates on Earth, only with unimaginable force. Over years, the magnetic tension builds until the crust can no longer hold. Then, in an instant, it fractures, a starquake unlike any other. When the crust cracks, the magnetic field rearranges violently, snapping and releasing pent-up energy in the form of intense bursts of X-rays and gamma rays. These bursts are brief, often lasting just fractions of a second, but they unleash more energy than our Sun will emit over 100,000 years. These starquakes are the magnetar's voice, a cosmic scream that travels across the galaxy. They are bursts of raw power, sending shockwaves that ripple through the star's magnetosphere and into interstellar space. From Earth, we detect these bursts as sudden spikes in high-energy radiation, cosmic flares that can disrupt satellites, interfere with radio communications, and briefly alter our planet's ionosphere. The most powerful magnetar flare ever recorded occurred in December 2004, when SGR 1806-20 erupted with such force that it was detectable despite being 50,000 light-years away on the far side of the Milky Way. The energy released was equivalent to 100,000 supernovae. Despite the vast distances, the effects reached Earth's atmosphere. Our planet's magnetic shield and ionosphere flinched under the impact, revealing how even these distant titans can affect us. Had the magnetar been a mere few dozen light-years closer, the consequences could have been catastrophic, disrupting electrical grids, damaging satellites, or even threatening life itself. Magnetars remind us of our vulnerability in the universe, even as they inspire awe with their cosmic power. Our understanding of magnetars has grown over the last few decades, thanks to advances in space telescopes and high-energy astrophysics. Instruments like the Fermi Gamma-ray Space Telescope and the Chandra X-ray Observatory have captured these bursts, providing crucial clues about their nature. Scientists study the timing, energy spectra, and recurrence patterns of magnetar bursts to unravel the complex physics at play, probing the limits of matter, magnetism, and quantum mechanics under extreme conditions. Each observation is a piece of a cosmic puzzle, revealing the behavior of matter under pressures and magnetic fields impossible to recreate on Earth. Inside the magnetar lies a remarkable state of matter. The core is thought to be a superfluid, an exotic phase where neutrons flow without friction, surrounded by a sea of superconducting protons that channel magnetic flux into concentrated tubes. This interior dance of particles and fields governs the magnetar's behavior, influencing when and how starquakes occur. Theoretical models suggest that over time, the magnetic field slowly evolves, causing stresses to build in the crust. The starquake is the crust's catastrophic response, a sudden realignment of the magnetic field and a violent energy release. The energy released during a starquake also accelerates particles trapped in the magnetosphere, charged particles trapped in the star's magnetic field. These particles spiral along field lines at nearly the speed of light, emitting radiation across the electromagnetic spectrum. This radiation, when it reaches Earth, allows us to study these events in unprecedented detail, painting a picture of one of the most extreme environments in the universe. Magnetars are a window into extremes, extreme density, extreme magnetism, and extreme energy release. They challenge our understanding of physics, pushing theories to their limits. They hint at the behavior of matter beyond nuclear density, at the interplay between quantum mechanics and astrophysics, and at the powerful forces shaping our universe. As humans, we gaze upward, humbled by these cosmic titans. Magnetars are reminders of our smallness, a testament to the universe's vast power and complexity. But they are also beacons of knowledge, illuminating the unknown and inspiring the pursuit of understanding. In their destructive quakes, we find clues about the fundamental forces that govern all matter. And in our quest to understand them, we find the resilience and curiosity that define us as a species. This is the story of cosmic quakes, of stars that break, not with silence, but with a thunderous roar that echoes across space and time. This is the power of the magnetar,